Hi everyone, welcome to this AP Environmental Science lecture on human population dynamics. So a few things before we get started. First off, I hope that you can't hear the fan behind me, and I hope that doesn't disrupt the recording in this video, but it is awfully hot in my office today, so there's a fan. Second thing is that we are going into the scary realm of social studies. So we are going upstairs into the social studies wing for this. So we're going to be talking about human populations today. We're going to be looking at, like I said, human population dynamics. We're going to be looking at topic 3.6, which is age structure diagrams. And the learning objective for that is just explain what they are. Topic 3.7, total fertility rate. The learning objective for that is explain factors that affect total fertility rate in human populations. And you'll notice that the enduring understanding for both of these is the same. Human populations change in reaction to a variety of factors, including social and cultural factors. And we have two other topics, topic 3.8 and 3.9, human population dynamics, which is explain how human populations experience growth and decline. And then the demographic transition. So just be able to define the demographic transition. Okay. And again, the enduring understanding for all of these is the same. Now, I will preface this by saying that a lot of this stuff should be review from your AP Human Geo course that you probably took as a freshman. If you did not take that class, then you probably took just CP Human Geo, and a lot of this is review from that as well. So a lot of it's review. I should also say that I am definitely not a social studies teacher. I'm not as familiar with all of the human stuff as I am with all of the science stuff, right? I'm a biologist by training, and I definitely look at populations from more of a biology perspective rather than a social studies perspective. So keep that in mind. The vocab is here. You guys can pause this now and jot this down or return to it later. Make sure you get everything. And we're going to start with Thomas Malthus. Thomas Malthus was a Brit from England in the 1800s. So remember that populations are limited by the available resources. Many of those we are going to call density dependent limiting factors. So it could be the amount of space, the amount of food, the amount of water, if it's a plant, the nutrients in the soil, the exposure to sunlight, whatever it is, density dependent limiting factors or limiting resources are going to limit that population size. And Thomas Malthus noticed that populations were growing throughout England and much of Europe, and that populations tend to grow at an exponential rate. However, he postulated that food production only grows linearly. And if you have a population that's growing exponentially that relies on food being there, and that food is only growing at a linear rate, right? There's only so much arable land, and you can only grow so many crops, and you can only take so much land on an island like Britain is. Food production is growing linearly. At this point, where there is this circle, there's going to be a Malthusian catastrophe. And that Malthusian catastrophe is essentially going to say that the population is going to outstrip its food resources, and it's going to lead to poverty and starvation, or starvation especially among the lower classes. It's going to lead to increased competition for that food. It's going to that starvation is going to weaken people, which is going to make them more susceptible to disease, and people are going to die, and that's going to cause the population to decrease below that food production line. This sounds very similar to what we discussed in the last PowerPoint with carrying capacity. So say that our carrying capacity is right here, so there's K. We could essentially have what we would call a Malthusian catastrophe right there, where we have our overshoot above that. Okay, so it's very similar. But we're not really going to talk a lot about how populations overshoot carrying capacity or Malthusian catastrophes today, because that was primarily in that carrying capacity lecture. Today we're going to talk mostly about dynamics and how populations change over time. Okay, so there is going to be a little bit of math in this. The math isn't too bad. It's basic algebra. The first equation that you guys are going to need is this one that's right here. So population change is the number of births plus immigrants minus the number of deaths plus emigrants. Okay. I'll show you a practice problem. You should be given most of these variables or all of these variables in many cases. And you should be able to calculate the population growth rate or the population change. Okay. Sometimes you'll see this as the number of people entering the population minus those exiting the population, right? Births plus immigrants is people entering, and deaths plus immigrants is people exiting that living population, okay? And I define immigrant and emigrant up there if you don't remember that from social studies, okay? So we'll plug in some numbers on the next slide. Populations are going to increase when your birth rate is exceeding your death rate. When your birth rate is higher than your death rate, your population is going to grow. Pretty straightforward, pretty simple. If you have more people being born than are dying, your population is going to increase. Your population is going to decrease when birth rate is less than death rate. Okay, so say that you have a devastating plague that's going through your population, say Europe during the 1300s, and many people are dying and a few people are being born. Your birth rate is pretty small, but your death rate is really big. So more people are dying and your population's decreasing. And your population is going to be stable if birth rates and death rates are equal. You can substitute immigrants and emigrants for birth rate and death rate here, or people entering the population and people exiting the population for birth rate and death rate here, and it'd be essentially the same thing. The other thing that I want to point out is on this graph. So this graph shows world crude birth and death rates from 1950 to 2010. What I want you guys to notice is that death rate is decreasing over time. So death rate in this red is decreasing and leveling off over time. And birth rate is also decreasing over time. Okay? But please note that birth rate is still higher than death rate. Okay? There's still more people being born on the planet than people dying on the planet. Okay? And we would typically in a societal sense call that good, right? But in a environmental sense, that may not be so great because that means that if the population is going to continue to increase, even though birth rate is declining, it is still higher than death rate is. Okay, so that difference right there is going to translate into a growing population. Okay, but I do want you to notice and please write down that birth rates have been decreasing globally over time. So let's talk a little bit more about birth rate and death rate. There's a couple ways that we can represent these values. One is by crude birth rate or crude death rate. Crude birth rate is the number of live births per 1,000 people per year. Okay? Crude death rate is the same thing. In order to get our percent birth rate, or what we would just call birth rate or death rate, we would convert these values to percentages. Okay? So for example, say that our crude birth rate is 42. On your AP test or on a test in my class, I say that crude birth rate is 42. I don't have to put any units on that, it's just 42. What that represents is 42 births per 1,000 individuals. And I can convert that into a birth rate or a percent by just converting it into a percent, doing the same thing that we always do to convert things by a percent. So 42 divided by 1,000 in this case times 100 gives us 4.2%. Now you'll probably see that there is a trick on this where you just move the decimal point one place, right? Because you are divided by 1,000 and then multiplying by 100, so that essentially cancels. 3 of those zeros, or I guess 2 of those zeros cancel, and you're dividing it by 10. Okay. However, I would caution you from doing the trick, from doing the shortcut method, because on the AP test you have to show every step of your work. So if you were doing this problem, you have to show this entire thing on the AP test, and you might as well just plug this entire formula into your calculator. Okay? So let's say that we have this problem. Calculate population growth rate for a developing country given that crude birth rate is 30.21, crude death rate is 7.98, and net migration is negative 6.47. There's a few things that I want you to point out, that I want to point out here, which is why I chose this problem. The first is that we're looking at population growth rate. So we're looking at a percent growth rate. Okay, they're not going to say percent growth rate, they're just going to say growth rate. The other one is this one, the net migration. So net migration is negative 6.47. If net migration, if your total migration, your immigrants plus your emigrants is negative, that means that there's more people leaving the population. So think about what that is for a second. Does that mean that it's an immigrants or higher rate of immigration or higher rate of emigration? So think about that for just one sec. Okay. So that would be a higher rate of emigration, people leaving the population. Okay, so your population is losing people, it is negative. So this is our formula. Our population growth rate is births plus immigrants minus deaths plus emigrants. Our birth rate is plugged in right here. So we can get 30.21 crude birth rate translates to 3.021% birth rate. Make sure that you keep all of your decimal points until we get to the very end. Don't round it in the middle of a problem. Keep all keep all digits to the very end. Our death rate, very similar, same thing. We just plug it in. And our migration is, we just plug that in also. Now we have to take these values and plug them into that equation. So the way that we do that, our percent growth rate is our births, so people entering the population, minus the people leaving the population. Notice what I did here. This is a plus, that's not a minus. Even though our migration is a negative rate, that just tells me that it goes into this value, that it's in that that term, that area within the parentheses. But I add those to the number of people that are dying or to the death rate. Okay, and all of that is subtracted from the people that are entering this population, the people being born. And for the answer, we get a percent growth rate of 1.576%. Okay, this is very representative of what you will see on an AP test or in a test in my class. All right. So what are some variables that can affect population growth rate? I split this into birth rate and death rate. We could also talk about immigration and emigration. However, we won't do it as much, but a little bit. Birth rate, that's going to be affected by children being needed as labor. So if children are used as a source of labor, then you're going to have more children, just in a societal scale, have more children to fill those jobs. Okay. Say that you are a farmer and you're rural, poor farmer in a developing country, and you can't afford to hire people to work on your farm, but you need those hands to work on your farm. Kids are a great source of labor on farms, right? You just have them go feed the chickens, get the eggs, milk the cows, etc. There's the cost of raising children. If the cost of raising children is high, that means that there's going to be less kids. All right. For example, in the US, raising a kid is very expensive. You have to, provide them medical care and dental care and clothes, and you have to pay for their sports fees and, their education and all of these things that go into the cost of raising kids. Food is huge. That's going to mostly cause people to have less kids. If the cost of raising kids is lower, then people can afford to have more kids. So if your kids are just, this is going to sound horrible, but if your kids are just dressed in rags and they're going without shoes and they're not getting an education and they're not playing any sports or activities or hobbies, anything that costs money, they don't have any toys besides what they can find out on the farm, then you can afford to have lots of kids because the cost of raising them is super low. Okay, so there's a negative correlation there, or an inverse correlation, I should say, sorry. Female education. So as females are educated and empowered, they tend to choose to have less kids. Okay, so the more that women are educated, the more power that women have, the more social freedoms that women have, the later that they're going to have kids, and the less kids that they're going to have throughout their reproductive lifespan. Okay, we'll actually talk about that in class, and I'll have you guys read an article. Okay. Access to family planning is also really big. So that includes just planning when you're going to have kids, when you're going to start to have kids, how many you're going to have, talk that out with your partner, all of that stuff. Access to contraceptives, access to birth control, access to abortions, all of that limits the number of children. Okay. Government policies can definitely affect the number of kids that people have. The most famous example and the largest scale example of that is China's one-child policy, but we'll again talk about that in class, so I'm not really going to talk about it too much here. And then religious beliefs, traditions, and cultural norms can either bring the number of kids up or bring the number of kids down, just depending on what those traditions are. Okay. Death rate, that's going to be influenced by life expectancy. So as people get access to modern medicine, and really a lot of this is modern medicine and stable food supplies. So life expectancy is going to increase as we get access to modern medicine, food supplies and distribution, better nutrition, improved sanitation, and safer water supplies. As that life expectancy increases, people are not only living into reproductive age, but they're living throughout their reproductive age and able to have more children. And then they're living beyond their reproductive age into old age. And they're still a mouth to feed, a person on the planet, even after their reproductive age, even, woman hits menopause at 45, 50, and then, lives to 90 years old. That's 50 years that, 45 or 40 years that she is using resources on the planet and causing the death rate to decrease. Okay. Maternal mortality rate, this is the number of mothers per 1,000 that die during childbirth. As you decrease the maternal mortality rate, you decrease death rate. Okay. There's also infant mortality rate, which is the number of infants that die, or per 1,000 that die before their first birthday. So that could be dying during childbirth. That could be dying anytime before their first birthday. Traditionally, before modern medicine, the infant mortality rate and the maternal mortality rate were very high. Okay, having a child is a very risky business without modern medicine, and maternal mortality rate was relatively high throughout all cultures before modern medicine. Infant mortality rate also very high before modern medicine. Children can starve. Children can, die of sudden infant death syndrome. Children are very susceptible to disease. So most children would die by disease before their first birth. Well, not most. Most children that died before their first birthday would die of disease and not other factors. Disease is a huge killer of children before modern medicine. You enter modern medicine and you enter stable food supplies, and those children survive. That decreases death rate, and that increases the number of people on the planet. Okay, and then obviously conflict and war. That could definitely increase your death rate. Okay, immigration and emigration. Immigration, people going into your country is going to be due to a lot of societal factors. So that's going to be, looking for jobs. That's going to be looking for, opportunity, education, a safe place to raise your children, away from war, away from conflict, away from political or religious persecution. Emigration would be the opposite of that. You are leaving a place because there's not a stable food supply. You're leaving a place because there's famine. You're leaving a place because there's not clean water for your kids. You're leaving a place to find a job to pay for your family to eat or to pay for your family's education. Okay, you're leaving a place just to get an education and to get better opportunity. Okay, or anything along those lines. So immigration and emigration are also affected by societal factors, but birth rate and death rate are the big ones here because they're typically the higher numbers in these calculations. Okay, and that leads us to total fertility rate. I'm going to try to say total fertility rate, which is abbreviated TFR. You'll see that on a lot of diagrams, but sometimes I'll just say fertility rate. It's the same thing. I'll probably never say absolute or potential natality. okay, but it's the same thing. This describes the reproductive potential of a human population. Okay, specifically, it's the average number of children per female over her reproductive lifetime. Okay, so you're not like tracking females. You're not like taking census records and like looking at like one woman over the course of her entire reproductive lifetime and at like saying how many is she having. You're doing this on a societal basis based off of medical records, hospital records, and you're averaging it over all the women in that society over their reproductive lifetimes. Okay. It's going to assume that her reproductively does not decline over her lifetime, which it does biologically speaking, and that she survives every reproductive event, which even with modern medicine is not a guarantee. And it's defined within the reproductive age, which is by international convention of 15 to 49. Sometimes you'll see it as 15 to 44, but 15 post-puberty when a woman can start to have children, and then 49, the average age of menopause when women stop to have children. Okay, and this is just a mathematical model, which you guys will luckily not have to do the math on this one, based on specific parameters in that society. Okay, so we're looking at how many women on average, how many children a woman in a specific society is expected to have over her lifetime. Okay, so to put a few numbers on that, right now the global total mean total fertility rate is 2.5. That means that all of the women around the planet right now at reproductive age are expected to have 2.5 children on average. Okay, obviously some women are going to have 0. Some women are going to have 5. Okay, and it's going to average out to be 2.5. Okay, around the world by country, it ranges from a low of 0.92 kids per woman in South Korea to just over 7 children in Nigeria, or a total fertility rate of over 7 in Niger. Sorry, not Nigeria, Niger. Okay, that was of November of last year is when I pulled that data. Okay, so let's just look at South Korea. Some women in South Korea are going to have 0 kids. Some women in South Korea are going to have 1 kid. Some women in South Korea are going to have 3 kids. Some women are going to have 4 kids. A lot of women are going to have between 0 and 1, maybe 2. All of this is going to average to 0.92. Okay. We could do the same example for Niger, where some women are going to have 5, some women are going to have 0, some women are going to have 9. All that's going to average out to be 7.03. Okay. Now, when we look at total fertility rate, we can look at some population dynamic stuff. We can see whether the population is growing or whether it is declining. Okay. Negative growth is going to be what I mean by declining or decreasing in size. If your total fertility rate is less than 2.1, you're going to have negative growth. That means that there's not enough kids in that population to replace the parents that are going to eventually die. Okay, so let's say that in a family, we're just going to traditionally say mom and dad, and they have 1 kid. Say that kid is a female. Okay, assume that there's no divorce, assume that there's no children outside that family. They have 1 child. Mom dies eventually, dad dies eventually. That 1 child does not replace 2 individuals. Okay, so your society is going to have a decreased population size if it's less than 2.1 total fertility rate. Total fertility rate of 2.1 exactly is going to be the replacement rate, assuming monogamy, and that's going to be a stable population. The reason that we use 2.1 rather than 2 is assuming that some individuals are going to die at childbirth or before reproductive age, and they're never going to have the chance to reproduce, right? There's some accident or an illness or something, and a child dies at age 9 before they reach reproductive age and can reproduce. Okay, so that's just kind of that little bit built in there, that 2.1 rather than 2.0. And then positive growth is going to be anything over 2.1. Okay, if you have 3 kids, you're not only replacing mom and dad, but you have an extra one in excess. Okay. All right. I shouldn't have said it that way. Um, if you're the third child, like not excess, you're not extra. I didn't mean it like that. I definitely don't know all the politically correct social studies terms to describe human populations. Again, sorry, biologist. Let's look at some values for the global population. Around 6000 BC, it's estimated that there was about 30 million people on the planet. This is after the dawn of agriculture, well into the civilizations and everything like that. So about 30 million people. Over 2,000 years ago, just over 2,000 years ago at 1 AD, it's estimated there's about 300 million people on the planet. And you see that from about 1,000 years ago to about 1750, well, let's just say 1550. It's pretty constant, okay? After 1550, the 1600s, the 1700s, it increases a little bit, but we're still below that billion people mark. We hit the Industrial Revolution and, you know, early stages 1800, later stages or mid into it 1850 when the consensus of its starting is, and it just explodes. After the Industrial Revolution, after global trade and digitalization and you know the medical advances that we've had in the past century, populations have just exploded, and we are right now at about 7.9 billion people. That's 7,900 million, but 7.9 billion. So just about hitting that 8 billion mark right there in 2022. Okay. This human population explosion is primarily due to higher life expectancy. So people are living longer, they're living older, so they're staying around on the planet longer, right? So there's just more people on the planet because they're living a longer lifetime. Okay. There's lower infant mortality rate. More children are surviving. In a culture that that traditionally had 7 kids, but 3 of them or 4 of them or even 5 of them were expected to die before reproductive age from diseases, especially or famine or anything. With those infant mortality rates, the culture hasn't shifted fast enough, and now like all of those kids, or maybe just one of all those kids are surviving, or maybe just one kid is dying before reproductive age, and now you have this exploding population size, and culture has not caught up to that. And then lower maternal mortality rate is definitely driving this as well. If a woman dies during her first childbirth, she can't have other kids afterwards because she's dead. So if that maternal mortality rate is decreased, she's living through the first birth, she's living through the second birth, she's living through the third birth, she's living through the fourth, and she can have 4, 5, 6, 7, 8 kids. Okay. So decreased death rate is the primary driver of the global population increase. Birth rate has also fluctuated globally, but it's not significantly increased. And like I said in that previous slide, it has decreased in many regions and worldwide. Okay, and this kind of gets us into age structures and age structure diagrams. But before we get there, I want to say that assuming that we have a constant death rate right now and we just locked in births globally to 2.1 children per woman, that means that populations would still continue to grow for another 50 years or more. Okay, that's due to something called population momentum, which we'll discuss a little bit later, but it's essentially saying that there's all these kids in the pre-reproductive age, you know, below 15 years old, that are eventually going to age into that reproductive age bracket, and they're also going to have kids. So I'll explain it a little bit more with some population pyramids or age structure diagrams, and you'll see what I mean about that population momentum. Okay. Get into these age structure diagrams. Now I'm going to try to say age structure diagrams. Yeah, I'm really going to try to say it. But a lot of the time I'm going to default to population pyramids because that's what I learned it as. But age structure diagram is what you'll see it on in AP environmental science. Okay, this is a graphical representation of a population per a given year. Okay, so for just a given year, and it's broken down by gender. So in this case, we have males on the left and females on the right. We definitely do want to break it down by gender. Say that there's something that goes on in this population. Say that there's a war and more men go out and fight than women do, and that population is going to be cropped off on that male side. Okay, we want to see how many males per female to female ratio there is, or female to male ratio, doesn't matter, the same thing. Okay, and then we have population down on the x-axis. We have our population in this case in millions. This would say that there's about 10 million males in this first bar and 10 million females. So individuals 0 to 5 years of age, there's 20 million of them if you count both males and females. Okay, and then we have increasing. In this case, in the middle is our y-axis, which is our age, up from 0 to 100. And you'll note that in this population, there's a lot of people that are 0 to 50. And then as people get older, it gets smaller because they're not expected to live to, 110, 120, etc. Okay. This can be interpreted to reveal a lot of things. The individuals gained in a population or expected to be gained in future. The individuals that are lost, you can even tell from this, although we won't do that in this class. You can tell the total fertility rate if we did some math, which we won't do in this class. And then what we will do is some long-term population trends, basically positive, negative growth, or stabilization. All right, so let's look at some examples. These are our 4 main types of population pyramids. We're going to have rapid growth over here on the left, and this is our classic pyramid shape. It's going to have a very wide base and then increasingly narrow top. Okay, this is definitely going to be very, very rapid growth. This is going to describe most developing nations. And what you're going to see is that there's a lot of people in your reproductive age bracket, but less and less as you get higher up in that reproductive age bracket. There's definitely less people in your old age bracket, your post-reproductive age bracket, and they're not expected to live as long as these people in these developed countries, okay? Because they're still getting access to modern medicine and things are still changing. Okay, but what I really want you to see is this base. This base is huge. And what this base is going to show, let's say in 5 years, everything gets shifted up, right? This is your 10 to 14-year-olds. They're going to shift up into your 15 to 20-year-olds. And that bar is going to get bigger in, let me shade it in this section. It's going to get bigger as those people shift up. And then those people shift up there, those people shift up there that year, and then you get an even bigger bar down here. That's going to be the people that are born from all of those folks that are reproducing. Okay, so every 5 years, this is going to get shifted up, or typically it's 5 years, just depending on the graph. It's going to get shifted up. So even if population growth rate was to decline right now in, say, Kenya or Nigeria or Saudi Arabia, you would still have all these people that need to age up into these reproductive age brackets that are going to reproduce, and they're going to perpetuate that big block down at the bottom. Okay, so that's what I meant by population momentum. All right, slow growth, your base is still wider than your your base is still wider than your reproductive age bracket. Okay, so you're going to have slower growth because it's not as wide as it is in the developing country. Okay, what we see here are industrialized countries, and either your fully developed or post-industrial countries. Okay, zero growth, your sides are just about vertical. Okay, so there's no population growth there. And then negative growth, your base is like a cone going in. Okay, kind of looks like an ice cream cone. I'm hungry, it's near lunch. So this is a declining population or a negative growth population. We don't use the term declining as much, but negative growth. All right. When you see a population pyramid that is very wide at the bottom, classic triangle shape, you know that that is a developing country. Okay, they tend to be growing very rapidly. A developed country tends to either be stable, growing at a very slow rate, or even at a negative rate. So we'll do this slide as a day starter in class, so I'll just skip this. And again, population momentum. So again, even if India in this case was to go to a total fertility rate of 2.1 children per woman, that still means that there's going to be this entire age bracket down here that's going to have to shift up throughout these ranks. And even if these kids are just going to have kids at a replacement rate value, then their population is still going to grow in terms of total number of individuals in that population. Okay, it might be that it eventually stabilizes many years down the line. Maybe I'll just redraw this up here. It eventually stabilizes down the line, but it's going to stabilize as a very large population. Okay. If that's not making sense, I'd recommend that you click this link. I'll link it in the description below. That will talk about population momentum in a little bit more detail, and they can do it in motion, which should really help. All right, and that leads us to our demographic transition model. I've talked about developing or industrial, et cetera. Let's talk about what those are. This is essentially a theory that describes the population change due to industrialization. There are 4 stages. There is pre-industrial. You could also, we'll just say pre-industrial. You might call that an agrarian, if I can spell. But there are many agrarian societies that are industrial. Agrarian just means that they're agricultural based, okay? But you won't see that, you'll just see pre-industrial. This is typically a small population. It's typically a stable population. You're going to have a high birth rate, but that high birth rate is going to be offset by a high death rate because of lack of access to modern medicine, lack of access to global food supplies and global trade and all of that stuff. Okay. Those societies are going to transition into the transitional stage, which you also might see as developing. Okay, this is going to be rapid population growth. This is your classical pyramid-shaped age structure diagram. Okay, rapid population growth because your high birth rate is no longer offset by a high death rate. The death rates are lower due to improved food and water security and healthcare. Okay, so access to modern medicine. Because this culture that was pre-industrial moves into this transitional stage, they still have high birth rates because that is culturally what they have done for thousands or tens of thousands of years. But all of a sudden, death rates are decreased, infant mortality rates decreased, maternal mortality rates decreased, and mortality rate in general has decreased. So there is going to be a massive population increase because of that high birth rate and low death rate. Okay. Then we transition into the industrial society. Growth rate is going to slow due to a low birth rate and a low death rate. So low death rate is going to remain, and it will probably even get lower. But finally, birth rate decreases and your population stabilizes. However, it stabilizes at a big population. Think India right now, or China right now, or even due to the land area, you can think of Mexico or like any country that's in this industrial stage tends to be a high population that's going to be a stable population. Okay, so their population pyramid is going to be very wide, meaning lots and lots of people, but it's going to have straight sides. And then you have your post-industrial. Your growth is going to stabilize or decline. Your birth rates are going to be equal and then fall below your death rates. Okay, so let's look at some examples, or an example of the diagram with population pyramids. So demographic transition, 5 stages. You notice that there's 5 stages here rather than 4. We'll talk about that in a second. So stage 1 is your pre-industrial. So pre-industrial, your birth rate is going to be very, very high. You do have a wide base to your population pyramid, but note that a lot of those individuals are dying before they reach their 15th birthday. Okay, they're not getting to reproductive age. So birth rate's high, death rate's high. These are more or less equal, and your population is stable. So your population is your total population here, and it is stable. It's staying the same size. In this case, just below birth and death rate per 1,000 people per year. So just like 9 per 1,000. Okay. Stage 2 is industrial. So birth rate stays high. Cultural norm, traditional, have lots of kids. Most of them are expected, or let's say, many of them are expected to die before their 15th birthday, but they all of a sudden don't, because now people aren't starving. Now you don't have famine every few years. Now you have modern medicine and water sanitation. So your death rate plunges or plummets. That means that your total population is going to increase. Okay? And it's going to do so rapidly. We get stage 3, and stage 3 is industrial. Your birth rate decreases, your death rate stabilizes down there, but note that birth rate is still much higher than death rate. Okay? So your birth rate does decrease, but it doesn't mean that it falls to 2.1. Not necessarily, it might, but it doesn't fall to the death rate. Okay, and that means that your population is going to increase, but at a slower rate. Okay. Stage 4 is mature industrial or post-industrial, my bad. Stage 4 is your post-industrial stage, and your birth rate and death rate might equal out. However, your population by this size is pretty big. Now, stage 5, some people will argue that there is a stage 5, some people won't. I tend to think that there is, but it's not in the AP standards. But just think about it as like post-industrial, okay? Or like, maybe the digital age or whatever. What's essentially going to start to happen here is that your birth rates are going to increase again, because they have to on a societal scale, just to keep stuff like Social Security and retirements in check. And people are going to start to have more kids than their parents did. So your population going to start to flare out down at the bottom and start to grow again. Okay, so you notice that the population starts to increase again. Okay, but you should be familiar with the demographic transition. Stage 1, 2, 3, and 4, definitely. You can probably, for our purposes, not really talk about stage 5 at all. And you should be able to correlate these stages with an age structure diagram, what's happening with birth rate and death rate, and what's happening with population growth rate, or your total population size, rather. So some ways to slow human population growth. Now, the first time that I taught AP Environmental Science, I just put this question out to the class. I was like, how can we reduce the number of people on the planet? And everybody was silent. And there was this one girl that very tentatively raised her hand, and she was like, you mean like genocide? And I was like, horror struck. And I was like, no, not genocide. How can we do this ethically? How can we slow or stabilize human population growth rate in a ethical manner? Okay, we absolutely cannot do it by violent means. That would be wrong. That would be morally wrong. Okay, what we can do though is any of these three options, especially in the developing world. Reducing poverty. As you reduce poverty, people tend to choose not to have as many kids. They tend to be better educated. They tend to not need children as part of their workforce. And those children tend to grow up and because they're educated, they tend to grow up and want to go into a career before family in general. Okay, maybe empowering women would be an example. So rather than traditionally marrying women off at the age of 15, like is being shown in the bottom right, you give women power in the society, and they can make their own choices. They can choose to have, choose when they marry. They can, at what age. They can choose to prioritize a career over family. They can choose to not have kids after a certain age or before a certain age. They can choose how many kids they have, right? So maybe shifting the power structure there. and then providing family planning and reproductive health care. Again, this is bare bones. We're going to talk about this a lot in class, so this is just kind of 3 options. However, with that, it has been shown that as women are educated, so this bottom left diagram, as more women are educated, so percent of girls enrolled in secondary school, the total fertility rate drops dramatically. Okay. As women become better educated, they tend to have less children than women that are not educated. Okay, and that's a pretty significant change from around a total fertility rate of 2 all the way up to a total fertility rate of 5.5. That's a huge difference. Okay, so just educating girls has definitely a positive impact. And then your Human Development Index. Human Development Index is essentially the quality of life. As you increase the Human Development Index, people tend to have less kids. So your societies that have the highest quality of life tend to not even have a total fertility rate of 2. Societies like South Korea, societies like Denmark or Germany or Finland tend to have very low total fertility rates compared to where the Human Development Index is rather low. Developing nations, especially if there's civil war and stuff like that, that makes life very, very hard for the average citizen, they tend to have lots of kids. And finally, let's end this with some more math. So the rule of 70, this is a simple formula that's going to determine the doubling time of a population if you know the population growth rate. Okay. This is a mathematical formula that you might see in economic class as well that can be used to determine the doubling time of like money with interest rates or something, but we're just going to do it with populations. It's very crude, it's very rough, but it does give you an estimate. So 70 is a constant. It's always 70 divided by your growth rate gives you your doubling time. Okay, so 70 divided by percent growth is doubling time. You can rearrange that formula to say 70 divided by doubling time gives you percent growth. Okay, just depending on what you're looking for. Let's say as an example, the US growth rate is currently 0.59%. In how many years will it double? Okay, 70 divided by 0.59%. In fact, we should not even have that percent. That's a typo. We do not have that as a percent there. 70 divided by 0.59 gives us 118.6 years. Okay, so that's how many years it would take for the US to double from a current population of 331 million to 662 million people, providing that conditions remain constant, which they obviously will not over the course of 118 years. Okay, but it's assuming that conditions don't change, assuming stable conditions. Okay. So a couple practice problems. Pause this now and do these 2 practice problems, and then we'll go over them. Okay, now that you're back, let's say for this first one, if India's population growth is currently 0.99%, how long will it take for the population in India to double from 1.38 billion people? Okay, and then what will the new population be that year? So our formula is 70 divided by our growth rate equals our doubling time. We can add 0.99 in for growth rate. 70 divided by 0.99 gives us our doubling time. Our doubling time is 70.71 years. So the Indian population is expected to, oops, I didn't do that last part. Okay, so the Indian population is going to be expected to double from 1.38 billion people to I'm doing this off the top of my head, 76 billion people. I think I'm right. Please feel free to correct me if I'm not. I'm definitely not, because that should be a 2. 2.76 billion people in 70.71 years. So if this is just adding on to the question, if this is 2022 right now, which it is, we add 70, I'm just going to say 70 years to that. We're expecting for there to be 2.76 billion people in India in 2092. Okay, so at the end of the century. Assuming that conditions stay constant, and assuming that this growth rate stays constant as well. Okay. Let's look down at the second one. The second one is kind of combining a lot of the math that we've done for this one question. So growth rate, number of births plus immigrants minus the death rate plus the immigrants. Sorry, I read that all wrong, but you see what it says. Okay, we have to convert our crude birth rates into percent birth rates. So I did that on the side. 13 divided by 1,000 times 100 gives me a birth rate of 1.3%, and then the other two for migration and death. Okay, our growth rate therefore is going to be 1.3 plus 0.1 in parentheses, subtracted by, or minus, not subtracted by, minus 0.6. Okay. Now notice the crude migration rate again is 1 out of 1,000 people. That is a positive number. So that means immigrants, people going into the population, which is why I added it there. Okay. Our growth rate is therefore 0.8%. Now, if these values remain constant, determine the year in which the population will reach 47 million. Right now it's at 23.5 million. So we know that that's one round of doubling. So 70 divided by our growth rate is our doubling time, 70 divided by 0.8 is our doubling time, 87.5 years is our doubling time. Okay, so determine the year that's going to happen. If this is 2022, which it is, plus 87.5, that would be what? 2099.5? Is that correct? Correct my math if I'm wrong. My math always sucks. I think it is wrong because that should be 2100. Math is hard. Yeah, 2100. I did have that animation. 2100.5. Okay. So thank you guys for sticking around to the end. Let's just go through these essential knowledge real quick. So for age structure diagrams, population growths can be interpreted from age structure diagrams by the shape of the structure. So again, you're looking at whether it's a pyramid, you're looking at whether it's like, kind of straight-sided or whatnot, okay? A rapidly growing population as a rule will have a higher proportion of young people compared to stable or declining populations. Moving on to total fertility rate. Total fertility rate is affected by the age at which females have their first child, educational opportunities for females, access to family planning, and government acts and policies. Again, we'll talk about this stuff in class a little bit more. If fertility rate is at replacement levels, recall that that is 2.1, a population is considered relatively stable. And factors associated with infant mortality rates include whether mothers have access to good health care and nutrition. Changes in these factors can lead to changes in infant mortality rates. Essentially, the higher health care and nutrition that they have, the lower the infant mortality rate, as well as the lower the maternal mortality rate. And then moving on to human population dynamics, birth rates, infant mortality rates, and overall death rates, access to family planning, access to good nutrition, access to education, and I can never say this word, postponement of marriage will affect whether a human population is growing or declining. Okay. Factors limiting global population include Earth's carrying capacity, so Malthusian Theory, right? And then that Malthusian catastrophe. Okay, we're potentially at that point. Go back to our carrying capacity lecture for that. Population growth can be affected by density independent or density dependent factors. So go back and check out the previous PowerPoint for that. And then the rule of 70, which you will have to do the math for. And then finally, demographic transition. Demographic transition, just be able to define it. It refers to the transition from high to lower birth and death rates, and then like moving from pre-industrial to industrial to post-industrial. Okay, typically a 4-stage system. However, in that diagram we had the 5 stages, but for AP you will only need to know the 4 stages. Okay, and then the characteristics of a developing country include higher infant mortality rates and more children in the workforce than a developed country. All right, hopefully you guys learned something new. Hopefully a lot of it was review from social studies. See you on class. Hope you have a good one. Bye.